Our reality is a three-dimensional shadow cast by something far greater. What you see and touch every day, the space you move through, might be just a thin slice of a cosmos with many more dimensions hidden from view. We are like characters in a vast cosmic story who can only read a single page. By the end of this journey, you will understand 30 incredible theories that physicists used to map these unseen depths. We will explore how entire universes could exist on membranes, why gravity might be leaking into other dimensions, and if our world is a holographic projection. What one question about the universe's true shape keeps you awake at night? The first attempt to map these unseen realms began a century ago, born from a simple and beautiful idea. In the 1920s, physicist Theodore Kaluza was studying Albert Einstein's equations of general relativity, which described gravity as the curvature of our familiar three dimensions of space and one of time. Kaluza had a radical thought. What if he rewrote those same equations but pretended the universe had one more dimension of space? The mathematics should have become more complex, but something miraculous happened. The equations split neatly into two parts. One part perfectly described Einstein's gravity. The other part perfectly described James Clerk Maxwell's equations for electromagnetism, the force behind light and magnetism. It was as if, by adding a single unseen dimension, Kaluza had found a secret room where gravity and light were actually the same force, viewed from different angles. But this raised an obvious and enormous question. If there is a fifth dimension, where is it? Why can't we walk into it or see it? This is where physicist Oscar Klein entered the story a few years later. He proposed a breathtakingly elegant answer. The extra dimension is not large and expansive like our own. It is unimaginably tiny, curled up upon itself in a loop smaller than an atom. Think of a garden hose. From a great distance, it looks like a simple one-dimensional line. But if you could shrink down to the size of an ant and crawl onto its surface, you would discover it has a second dimension curled around its circumference. We are like those distant observers, too large to perceive the microscopic curled-up dimension that Klein proposed. This idea is called compactification. In the Kaluza-Klein theory, every single point in our familiar four-dimensional spacetime contains this hidden, looped fifth dimension. We don't perceive it because we are, in a cosmic sense, too big to take the trip around it. For a time, this theory promised a grand unification of the cosmos's forces, a single mathematical framework explaining everything, but the dream eventually faced serious challenges. New forces were discovered, like the strong and weak nuclear forces that operate inside atoms, and the simple five-dimensional model could not easily accommodate them. The theory also struggled to make testable predictions that differed from our standard physics. Yet its legacy is profound. Kaluza and Klein planted the seed. They showed that adding hidden dimensions wasn't just science fiction. It was a mathematically coherent possibility that could solve deep puzzles. They gave physicists permission to think bigger, to ask what other secrets might be folded into the fabric of reality, waiting to be unfurled. That seed of an idea from Kaluza and Klein lay dormant for decades, a fascinating mathematical curiosity with no clear home in the real world. Then, in the late 20th century, a revolutionary new framework breathed astonishing new life into it. This is superstring theory, a vision so radical it redefines the very nature of reality's building blocks. Forget the idea of tiny, solid points like electrons or quarks. Superstring theory proposes that at the most fundamental level, everything is composed of unimaginably small, vibrating loops of energy. Think of a violin string. Pluck it one way and it produces a specific musical note. Pluck it another way and the note changes. In superstring theory, each distinct vibration pattern of these energy strings corresponds to a different fundamental particle. One vibration is an electron, another is a photon of light, another is a quark. The entire symphony of the universe arises from the harmonics of these strings. But there is a profound catch, a requirement written into the mathematics itself. For the equations of superstring theory to be consistent, to avoid nonsensical infinities and contradictions, the strings cannot vibrate in just our familiar 3 dimensions of space and 1 of time. They require a stage with 10 dimensions. That means 6 additional spatial dimensions beyond our perception must exist. So where are they? Following Klein's old idea, physicists believe these 6 extra dimensions are compactified, curled up into an unbelievably complex geometric shape at every single point in our spacetime. These shapes are known as Calabi-Yau manifolds. Picture the most intricate, multi-dimensional snowflake you can conceive, a shape with holes and twists and folds in 6 dimensions. The specific geometry of this hidden Calabi-Yau manifold is everything. Just as the shape and size of a violin's body determines the quality of its sound, the exact geometry of these curled-up dimensions dictates how the strings vibrate. This, in turn, determines the properties we observe in our 3-dimensional world, the masses of particles, the strengths of forces, even the number of particle families. In this breathtaking view, the entire diversity of our cosmos, every law of physics we measure, is an echo of the hidden geometry of dimensions we cannot see. The search for the one true Calabi-Yau shape that describes our universe is one of the greatest quests in theoretical physics. But the story of strings does not end with 10 dimensions. For all its beauty, superstring theory presented physicists with an unsettling puzzle. By the 1990s, researchers had developed not 1, but 5 distinct and seemingly self-consistent versions of the theory. Each had 10 dimensions and vibrating strings, but their mathematical details differed. It was as if 5 different maps all claimed to describe the same hidden continent, yet none of them matched. Which one was correct? The answer arrived not with a solution, but with a deeper, more mysterious framework. It is called M-theory, and it is arguably the most enigmatic idea in modern physics. M-theory revealed that those 5 string theories were not rivals. They were different faces of a single, grander structure, and to see that unity required adding 1 more dimension. M-theory lives in 11 dimensions. This extra dimension is not curled up like the others in a Calabi-Yau shape. Instead, it opens up a radical new way of thinking. In this 11-dimensional realm, the fundamental objects are not just 1-dimensional strings. They can also be 2-dimensional sheets or 3-dimensional blobs or even higher dimensional objects. These are called membranes or branes for short. Think of it like this: a string is a 1-brane, a sheet or membrane is a 2-brane. Our entire 3-dimensional universe could astoundingly be a 3-brane. This is the revolutionary leap. In M-theory, our cosmos might not be all there is. It could be a vast 3-dimensional island, a floating membrane adrift in a higher dimensional space called the bulk. The other 6 dimensions are still curled up tightly on our brain, but this new 11th dimension provides the arena in which brains can exist and move. The 5 string theories we started with are simply different perspectives on M-theory, seen when one looks at this 11-dimensional picture from different mathematical angles or under different conditions. They are all part of the same map. This idea that our universe is a brane has breathtaking consequences. All the particles we know and love, like electrons and quarks, could be open strings whose ends are stuck to our brain like pins on a bulletin board. They cannot leave our 3-dimensional slice of reality, but one entity might be able to escape into the bulk, gravity. This leads us to our next profound mystery, a theory that could explain why the force that holds galaxies together is so inexplicably weak. Gravity feels weak because it is not entirely here with us. In our daily lives, gravity seems powerful, holding planets in orbit and pinning us to the ground. But compared to the other fundamental forces, it is astonishingly feeble. A tiny refrigerator magnet can overcome the gravitational pull of the entire Earth, lifting a paperclip against that immense planetary force. For decades, physicists have asked why. The Brane world scenario offers a startlingly elegant answer. It proposes that our universe is not an isolated island, but a three-dimensional membrane, a three-brane, floating within a higher dimensional space called the bulk. All the particles of the standard model, the electrons, quarks, and photons that make up matter and light, are like tiny vibrations confined to the surface of this membrane. Their strings are anchored here so they cannot leave. This is why we perceive only 3 dimensions of space. We are, in a very literal sense, stuck on the brane. But gravity is different. In the framework of M-theory, gravity may arise from closed loops of string, vibrations with no ends to pin them down. These closed strings could slip off our brane and propagate freely into the extra dimensions of the bulk. Imagine our 3-dimensional universe as a vast sheet of paper suspended in a thick fog. The ink on the paper, representing all matter and light, stays firmly on the surface. But if you spill water on the paper, it soaks in and also evaporates into the surrounding fog. The water is like gravity, diffusing into a much larger volume. From our perspective on the paper, the water seems weak because most of it has drifted away. This leakage into the bulk could explain gravity's puzzling feebleness. Its strength is not inherently weak, it is simply spread thin across dimensions we cannot access. The force we feel is just the tiny fraction that remains on our brane. This idea transforms our cosmic self-image. We are not at the center of everything. We are inhabitants of a single surface in a far grander, multidimensional architecture. Other branes, other entire universes with their own laws of physics, could be floating mere millimeters away in the bulk, completely invisible to us because their light and matter are trapped on their own membranes. The only hint of their existence might be a subtle, ghostly tug through the one thing that can cross the divide, the gentle, leaking force of gravity. This idea of gravity leaking away was so compelling it demanded a bold new picture. In 1998, physicists Arkani-Hamed, Dimopoulos, and Dvali made a radical proposal. They asked, what if we have been thinking about the extra dimensions all wrong? What if they are not all curled up into a space trillions of times smaller than an atom? Their model, now known by their initials ADD, suggested one or more of these extra dimensions could be surprisingly large, perhaps as big as a millimeter across. To our human senses, a millimeter is still vanishingly small, but in the world of particle physics, it is an astronomical distance, a vast new landscape. This single shift in perspective offers an elegant solution to the hierarchy problem, the puzzle of why gravity is so weak compared to the other forces. The explanation is one of geometry and dilution. In our familiar 3-dimensional world, the strength of gravity diminishes with the square of the distance. This is the famous inverse square law, but if gravity can also spread into one or more large extra dimensions, its lines of force would spread out into a higher dimensional volume. Imagine the difference between a light bulb in a small room and that same bulb in a gigantic warehouse. In the small room, the light is intense and bright everywhere. In the vast warehouse, the light becomes diffuse, dimming to a faint glow. In the ADD scenario, the fundamental strength of gravity is not actually weak. It might be just as potent as the other forces at their core, but because it has access to these large extra dimensions, its true intensity is diluted by the time it reaches us in our 3-dimensional slice. We are only feeling a faint shadow of its full power. This leads to a stunning and testable prediction. If there is a large extra dimension, the inverse square law we take for granted should break down at very small distances, precisely at the scale where gravity can begin to spread into that new dimension. For over 2 centuries, since the time of Henry Cavendish, scientists have measured gravity's pull with incredible precision. The ADD model sent experimental physicists on a new kind of treasure hunt. building exquisitely sensitive devices to measure the gravitational attraction between objects separated by mere fractions of a millimeter. They are looking for a tiny deviation, a whisper that gravity's behavior changes when you look closely enough, a sign that we are brushing against the edge of another, larger reality. While no definitive signal has been found yet, the search continues, pushing the boundaries of how finely we can probe the fabric of space itself. The search for large extra dimensions is a thrilling one, but it is not the only path. Another profoundly elegant theory emerged at nearly the same time, offering a different kind of geometry to explain gravity's feebleness. This is the Randall-Sundrum model, named for physicists Lisa Randall and Ramon Sundrum. Their vision is not of a large, flat extra dimension, but of a warped one, a cosmic landscape of staggering extremes. Imagine a universe with 5 dimensions in total. 4 are our familiar space-time, and the 5th is a single, finite extra dimension, a short bridge between 2 walls. These walls are 3-dimensional branes floating within this 5-dimensional bulk. Our entire universe exists on one of these branes, often called the weak brane. The other brane, at the opposite end of the short bridge, is known as the Planck brane, the domain of fundamental quantum gravity. What makes this model so powerful is what happens in the space between them. This 5th dimension is not empty. It is filled with a uniform negative energy, a kind of cosmic tension that warps the geometry of space itself. This warping is exponential, meaning its effects increase dramatically over a very short distance. Picture a rubber sheet. If you place 2 objects on it and then press down heavily in the middle, the sheet will dip into a steep valley. The distance along the curved surface of the valley between the 2 objects is much greater than the straight line distance through the air. The Randall-Sundrum model creates a similar but far more extreme warping of the very fabric of reality along that 5th dimension. Because of this intense curvature, the scale of energy and mass changes exponentially as you move from one brane to the other. On our brane, the weak brane, everything appears at the low energy scale we observe. The mass of a proton, the strength of gravity, all seem ordinary. But on the distant Planck brane, the fundamental scales are the true, unimaginably high values dictated by quantum gravity. The genius of this setup is that gravity, which permeates the entire 5-dimensional bulk, feels this warping deeply. A gravitational wave originating from the Planck brane, where gravity is naturally strong, becomes exponentially diluted or redshifted as it travels across the warped geometry to reach our brane. By the time it arrives here, its strength has been suppressed by that enormous warp factor. So gravity seems weak to us not because it leaks into a large volume, but because we live in a dramatic gravitational lowland, a quiet valley far removed from the towering peaks of fundamental energy. All the fury of quantum gravity is confined to the distant shore of the Planck brane, while we experience only its faint, gentle echo. This elegant warping accomplishes the same goal as large extra dimensions, but within a space that can be microscopically small, offering a compelling and beautiful alternative map of the hidden architecture behind our reality. These warped geometries and floating branes lead us to a profound question about beginnings. What if our universe did not start with a single, explosive Big Bang from a point of infinite density? What if it began with a crash? This is the core of the ekpyrotic universe model, a theory that rewrites the cosmic origin story using the language of branes and extra dimensions. In this picture, our 3-dimensional universe is once again a vast membrane, but it is not alone. There exists another parallel brane, a ghostly twin universe, floating a microscopic distance away in the higher dimensional bulk. For an immense period, these 2 branes are slowly, almost imperceptibly, moving toward each other across that hidden dimension. This long, drawn-out approach is the ekpyrotic phase, a term from ancient Greek philosophy meaning out of fire. It is a phase of slow, gentle contraction, not of space itself, but of the separation between the worlds. There is no singularity, no point of infinite anything, just a gradual coming together. Then they touch. The collision between these two three-dimensional worlds along their entire infinite expanse is what we perceive as the Big Bang. The immense kinetic energy of the impact is converted into the seething hot soup of matter and radiation that filled the early cosmos. It was not an explosion from a point, but a flash of creation across an entire pre-existing plane. This elegant scenario offers compelling solutions to long-standing cosmological puzzles. Take the horizon problem. Our universe's cosmic microwave background, the afterglow of the Big Bang, is incredibly uniform in temperature in all directions. Yet, in a standard Big Bang model, distant regions of the early universe would never have had time to exchange heat and equalize. How did they know to be the same temperature? In the ekpyrotic model, the answer is beautiful. Before the collision, the two branes existed for an eternity. They had all the time in the world, literally, to settle into a smooth, uniform state. The collision then imprinted that uniformity onto the newborn hot universe, explaining its perfectly even starting temperature without needing a separate period of hyper-fast inflation. But the story can become even grander. This model naturally suggests a cyclic universe. After the fiery collision, the branes rebound, moving apart and expanding, filled with the new universe they've created. Eventually, the expansion stops, and the attraction between the branes pulls them together once more across the dark bulk. They will collide again, sparking a new Big Bang and a new cosmic cycle. In this breathtaking vision, our universe is not a one-time event. It is the latest chapter in an endless, rhythmic dance of creation and rebirth, where parallel worlds meet in the hidden dark to give birth to light over and over again across eternity. Yet if our universe is a membrane born from a collision, what is it truly made of? The answer might be something even more astonishing than matter or energy. It might be made of information. This brings us to one of the most radical ideas in all of physics, the holographic principle. It proposes that all the information describing everything within a volume of space, every star, every planet, every person, can be perfectly encoded on the two-dimensional boundary that encloses it. Our rich, three-dimensional reality, with all its depth and texture, could be a holographic projection from data painted on a distant, flat surface. The roots of this mind-bending concept are found in the most extreme places in the cosmos, black holes. In the 1970s, physicist Jacob Bekenstein discovered that a black hole's entropy, which is a measure of its hidden information or disorder, is not proportional to its volume as you might expect. Instead, it is proportional to the surface area of its event horizon, the point of no return. It was as if all the data about the matter that fell into the black hole was not lost inside, but was somehow smeared across its two-dimensional surface. Stephen Hawking later showed that black holes can evaporate, raising a terrible paradox. If the black hole disappears, what happens to all that information? The holographic principle emerged as a daring solution. It suggests the information is never actually inside the black hole in the first place. It was always on the surface, and the three-dimensional interior we imagine is a construct, a hologram generated from that surface data. String theory provided a concrete mathematical realization of this idea. In a landmark paper, physicist Juan Maldacena described a universe where a version of string theory operating in a warped five-dimensional space is completely equivalent to a quantum field theory living on its four-dimensional boundary. This is known as the AD/CFT correspondence. It is a precise dictionary translating between a higher dimensional world with gravity and a lower dimensional world without it. While our universe is not exactly this model, the implication is profound. It suggests that the laws of physics do not require the dimensions we experience to be fundamental. The true, fundamental description of reality might exist on a lower dimensional surface, a cosmic film, and everything we are, everything we see, is a magnificent three-dimensional projection. The screen you are looking at right now, your own sense of touch and depth, the vast distances between galaxies, all of it could be an incredibly convincing illusion generated from a two-dimensional code written at the edge of space. This forces a staggering philosophical question. Is our reality, with all its visceral solidity, fundamentally lower dimensional? Are we, in essence, living inside a hologram? Geometry holds the master key to our universe's laws. To understand how, we must return to that core idea of compactification, the process that hides extra dimensions from our view. The concept is simple in principle but profound in its consequences. Imagine you are an ant living on the surface of a long, thin garden hose. If you are a very small ant, you have two distinct directions to travel. You can crawl along the hose's length, and you can also crawl around its circular circumference. For you, the hose is a two-dimensional surface, but now picture a human observer standing far away. To their eyes, the hose appears as a mere one-dimensional line. They cannot perceive the tiny, curled-up circular dimension that you, the ant, experience so intimately. This is the essence of compactification. The extra dimensions predicted by string theory are not missing. They are simply curled up into loops or shapes so incredibly minute that, at our macroscopic scale, they are invisible. Every single point in our familiar three-dimensional space is not truly a point. It is the opening to an entire hidden micro-universe of 6 additional spatial dimensions. The mathematical shapes that describe these curled-up spaces are known as Calabi-Yau manifolds. These are not simple circles or spheres. They are intricate, 6-dimensional shapes with a specific and beautiful property that allows the strings of superstring theory to vibrate consistently. Picture a snowflake, but one whose symmetry and complexity exist in 6 dimensions, with folds, holes, and tunnels in geometries far beyond our ability to visualize. The exact form of this Calabi-Yau manifold is everything. It acts as the resonant chamber for the vibrating strings, just as the shape and size of a guitar's body determine the notes it can produce. The specific geometry of the Calabi-Yau manifold dictates the possible vibration patterns of the strings. Each distinct vibration corresponds to a different fundamental particle. One particular resonant pattern might give rise to an electron with its specific mass and electric charge. Another, slightly different pattern dictated by the manifold's twists might produce a quark. The strength of the forces we observe, like electromagnetism and the nuclear forces, are also set by this hidden geometry. In this breathtaking framework, the physicist's quest transforms into a geometric one. The search for the fundamental laws of nature becomes a search for the one true Calabi-Yau shape. Finding it would mean discovering why our universe has the particles it does, why forces have the strengths they possess, and why reality looks exactly the way it does. The diversity of everything we see may simply be the unique echo of a 6-dimensional shape folded into the heart of every point in space. But if particles are vibrations anchored to a surface, what is that surface made of? It is not a passive stage, but a dynamic, living part of the cosmic drama. These surfaces are called D-branes, and they are the homes where matter is born. In string theory, there are 2 fundamental types of strings. Closed strings are loops with no ends, and as we've seen, these often correspond to gravity. Open strings are segments with 2 distinct endpoints. For decades, a puzzle lingered. What do these endpoints attach to? The answer revolutionized the field. The endpoints of open strings are fixed to D-branes. The D stands for Dirichlet, a type of boundary condition in mathematics, but you can think of a D-brane as a dimensional anchor. A D0 brane is a point, a D1 brane is a line, a D2 brane is a sheet. Our universe in many models could be a vast D3 brane, a 3-dimensional membrane where the ends of open strings are stuck like pins in a cosmic corkboard. This is a profound shift. These branes are not just abstract geometry, they are physical objects with mass, tension, and the ability to vibrate and move through the higher dimensional bulk. They are the stages upon which the particles of our world perform. Every electron, every quark, every photon of light we know is represented by an open string whose specific vibrational pattern is determined by how it is anchored and stretched on its D-brane. The properties of the brane itself, its dimension and how it is embedded in the extra dimensions, dictate what kinds of strings can exist on it, and therefore what kinds of particles and forces can manifest in that universe. This gives physicists a powerful new language for cosmology. The Big Bang itself could be modeled not as an explosion from a point, but as the collision or interaction of 2D branes. When they meet, the immense energy of the impact could excite a frenzy of open strings on their surfaces, populating a new universe with particles and radiation. Even the process of cosmic inflation, the rapid expansion of space, can be described as a D-brane slowly relaxing and flattening out in the higher dimensional space. In this view, D-branes provide the tangible architecture of reality. They are the continents in the hidden dimensions, and we, along with all the matter we are made of, are intricate patterns etched upon their surface, vibrations anchored to a stage that is itself alive and moving through a grander, unseen dark. The search for that one perfect Calabi-Yau shape may be a quest without a single answer. Instead of a unique solution, string theory presents us with a dizzying, almost infinite array of possibilities. This is the infamous landscape problem. Because of the many different ways the 6 extra dimensions can be curled and twisted into a Calabi-Yau manifold, and the countless ways that fields like electromagnetism can be woven through that geometry, the mathematics does not point to one universe. It points to a number so vast it defies human comprehension, 10 to the power of 500 possible stable configurations. That is a 1 followed by 500 zeros, a number greater than all the atoms in our observable universe. Each of these configurations represents a different possible vacuum state, a different set of physical laws, a different universe with its own particles, forces, and constants. In this landscape, our cosmos is not special or inevitable. It is simply one garden in a cosmic archipelago of unimaginable variety. Some universes in this landscape might have 4 large spatial dimensions, others might have 7. Some might have gravity 1,000 times stronger, snuffing out stars instantly, or electromagnetism too weak to ever form atoms. The vast majority of these possible worlds would be sterile, hostile to any form of complex structure, let alone life. This leads to a profound and controversial question. If our universe is just one random possibility among a near infinity of others, why does it have the precise, finely tuned properties that allow galaxies, planets, and conscious observers like us to exist? One proposed answer is the anthropic principle. In its simplest form, it states that we can only observe a universe that is compatible with our existence. We shouldn't be surprised to find ourselves in a universe with 3 stable spatial dimensions and constants that allow for carbon-based life, because in all the universes where those conditions are not met, there is no one around to be surprised. It is not that the universe was designed for us, but rather we are a product of its specific, life-permitting lottery ticket. The landscape and the anthropic principle shift the goal of fundamental physics. The dream of a single, elegant equation that uniquely predicts everything about our world may be replaced by a statistical understanding. We may live in a multiverse where every mathematically consistent set of laws plays out somewhere in the vastness of reality or the endless flow of time, and our story is written on just one of its countless pages. This near infinity of possible universes in the string theory landscape presents a profound challenge. How can we ever test such an abstract mathematical idea? Remarkably, physicists have discovered a powerful bridge between these speculative realms and problems we can actually solve. It is called the anti-de Sitter conformal field theory correspondence, often shortened to AD/S/CFT. This is not just another theory, it is a precise mathematical dictionary, a duality that translates between two seemingly different worlds. On one side of this cosmic dictionary, you have a universe with gravity. Specifically, it is a warped, higher-dimensional space known as anti-de Sitter space, or AdS. Think of it as a cosmic saddle shape, a universe with a negative curvature that naturally contains black holes and the full force of Einstein's gravity. This is the AdS side. On the other side, you have a quantum field theory living on the boundary, the outer skin, of that warped universe. This boundary has one less dimension. A quantum field theory is our most successful framework for describing particles and forces, like the theory of quarks and gluons that make up atomic nuclei, but it famously does not include gravity. This boundary theory is conformal, meaning it looks the same at all scales, possessing a perfect symmetry. The AdS/CFT correspondence states that these two descriptions are completely equivalent. They are two different languages telling the exact same story. Every single phenomenon in the warped gravitational interior has a perfect translation into the language of particles and forces on the lower dimensional boundary, and vice versa. This is the concrete mathematical realization of the holographic principle. The three-dimensional interior, with its black holes and gravitational waves, is a holographic projection from the two-dimensional quantum data painted on its boundary. It is as if the entire plot of a complex, three-dimensional movie is encoded without any loss on a two-dimensional DVD. The DVD is the boundary quantum field theory, and the immersive movie experience you watch is the gravitational universe. This duality is more than a philosophical marvel, it is an incredibly powerful calculational tool. Some problems in our universe are notoriously difficult to solve, like understanding the behavior of the super-hot, super-dense quark-gluon plasma created in particle colliders. This is a strongly coupled system where particles interact so fiercely that traditional math breaks down. But through the AdS/CFT dictionary, physicists can translate that intractable problem into a different question about gravity in a hypothetical warped space where the mathematics of black hole thermodynamics can provide clear answers. They solve the gravity problem in the higher dimensional hologram, then translate the result back to understand the real-world quantum system. In this way, a theoretical map of hidden dimensions becomes a practical key, unlocking mysteries in our own world and offering our strongest hint yet that reality may indeed be a magnificent, lower-dimensional illusion. While string theory paints a cosmos of vibrating strings and holographic brains, a radically different school of thought asks us to rebuild reality from the ground up. This is causal dynamical triangulations, a theory that doesn't assume the existence of smooth, continuous space and time at all. Instead, it proposes that the fabric of our universe is woven from an enormous number of tiny, indivisible building blocks. Picture the most basic geometric shape you can have in any dimension. In 2 dimensions, it's a triangle. In 3, it's a tetrahedron, a pyramid with a triangular base. In 4 dimensions, the shape is called a 4-simplex. The theory takes vast numbers of these 4-dimensional simplices and glues them together along their triangular faces, following very specific rules. This process is called triangulation, and it's like constructing a fantastically complex, multidimensional mosaic. But there's a crucial guiding principle: causality. Every simplex has a clear before and after. Time at this fundamental level has a defined direction, preventing the kind of chaotic, nonsensical geometries where time loops back on itself. This rule imposes order on the quantum frenzy. At the tiniest scales, this mosaic is not smooth. It is a churning, frothing sea of geometric possibilities, a quantum foam where these simplices constantly fluctuate, connecting and disconnecting in a probabilistic dance. This is the true, fundamental state of the universe according to this theory, a soup of geometric pieces in many dimensions with no predefined structure. The miracle happens when you zoom out. Physicists run colossal computer simulations, allowing these causal triangulations to evolve according to the rules of quantum mechanics. And something astonishing emerges from the chaos. Without being programmed to do so, the simulation spontaneously forms a smooth, classical universe that has exactly 4 large dimensions, 3 of space and 1 of time. The microscopic, higher-dimensional soup crystallizes into the familiar macroscopic world we inhabit. It's as if you gave a child a box containing a chaotic mix of Lego bricks in all shapes and sizes, and after shaking it for long enough, it spontaneously assembled itself into a perfect, sturdy castle. The dimensions we experience are not fundamental. They are collective properties, emergent phenomena that arise from the statistical behavior of trillions upon trillions of tiny geometric parts. This offers a powerful and elegant alternative path to understanding where dimensions come from. They are not hidden or curled up. They are born from the bottom-up organization of spacetime's own atomic pieces. While one path builds from tiny strings, another rewrites the rules of geometry entirely. This is loop quantum gravity, the great conceptual rival to string theory. It asks a different kind of question. If the other forces of nature are quantized, emerging in discrete packets like photons of light, why should the stage itself, the fabric of spacetime, be smooth and continuous? Loop quantum gravity proposes a radical answer. Space itself is made of atoms. In this theory, there are no extra dimensions to curl up or hide. Instead, it takes our familiar 4-dimensional spacetime and breaks it down into its most fundamental, indivisible pieces. You cannot divide a volume of space infinitely. There is a smallest possible volume, a tiny grain of reality, just as there is a smallest possible unit of electric charge. Area 2 is quantized. There is a smallest possible patch of surface area in the universe, a fundamental pixel of geometry. These quanta of space are not floating in a void. They are woven together into a dynamic web called a spin network. Picture a vast, constantly changing graph. The lines or edges of this graph represent the smallest quanta of area. The points where lines meet, the vertices, represent the smallest quanta of volume. Each line carries a label, a number called a spin, which tells you the precise size of that elemental area. The entire structure hums with quantum uncertainty. The network is not static, it evolves, its connections changing in discrete jumps, and this evolution is what we perceive as the smooth, continuous flow of time. In loop quantum gravity, spacetime is not a backdrop. It is this living, breathing, quantum mechanical entity. Now, where do dimensions fit into this discrete tapestry? Loop quantum gravity does not start with extra dimensions, but its mathematical framework opens a fascinating door. The spin network itself exists in a kind of abstract, background-free space. It is not embedded in a pre-existing arena. The network is the arena. However, to visualize its structure and how our familiar 3-dimensional geometry emerges, physicists often represent these complex graphs as existing in a higher dimensional abstract space, much like how a 3-dimensional model of a social network can help us see connections that are hard to grasp in a flat list. More concretely, some research explores how the quantized geometry of loop quantum gravity could be the underlying structure of a brane in a brane world scenario. Imagine our 3-dimensional brane is not a smooth sheet, but is fundamentally this shimmering, discrete spin network. The brane is its geometry. This opens a potential bridge between these two grand theories, where the atomic structure of space in loop quantum gravity provides the substance for the membranes of string theory. Here, the quest is not to find hidden dimensions, but to understand how the dimension we experience is built, stitch by quantum stitch, from a network with no location at all. The idea that dimensions can crystallize from chaos or be woven from quantum threads forces us to confront a deeper mystery. Where do all the possibilities go? Every choice you make, every quantum particle spin, creates a fork in the road of reality. According to one of the most audacious interpretations of quantum mechanics, they don't vanish. They all happen. This is the many worlds interpretation, and when it collides with the cosmology of hidden dimensions, it creates a vision of reality so vast it defies comprehension. In the standard quantum story, a particle exists in a haze of possibilities, a superposition, until it is observed. At that moment, the wave function collapses and we see a single, definite outcome. The many worlds interpretation rejects this collapse entirely. Instead, it proposes that every single possible outcome of a quantum event actually occurs. The universe doesn't choose, it splits. When a particle can spin either up or down, the universe bifurcates like a branch splitting on a tree. In one branch, you measure spin up. In the other, an identical version of you measures spin down. Both branches are equally real, but they decohere, becoming forever separate and non-interacting. We only experience one timeline, one continuous thread of consciousness, but a near infinity of other versions of us are living out every conceivable alternative in parallel worlds. Now weave this quantum tapestry into the fabric of Brane cosmology. Where do all these branching worlds physically reside? Could each quantum branch be its own slightly different three-dimensional brane floating in the bulk? Or perhaps the branching itself occurs within a higher dimensional landscape, where every possible configuration of our universe's laws, every twist of the Calabi-Yau manifold, is realized in some distant branch. In this staggering synthesis, the multiverse becomes a double-layered marvel. On one level, you have the spatial multiverse of Brane's entire cosmic islands with different physical constants. On another level, superimposed upon each of those islands, you have the quantum multiverse, constantly splitting into countless variations of history. In one brane, gravity is strong and stars are short-lived, but within that brane, there are branches where life never arose and branches where it took a completely alien form. Your double in another brane might be made of different particles, while their quantum double is making a different choice at this very moment. This isn't just a multitude of worlds. It is an ensemble of multiverses, a fractal cascade of possibilities where every what-if is not just a story, but a physical place. The branching dimensions of quantum possibility and the hidden spatial dimensions of cosmology could be two sides of the same coin, a single architecture for housing every possible version of everything. But if gravity can slip between worlds, what messenger carries its signal? To understand the leak, we must meet the particle that would make it all possible, the graviton. In our quantum picture of the world, every force is transmitted by a fundamental particle. Light is carried by photons. The nuclear forces are carried by gluons and W and Z bosons. For gravity to be unified with these other forces, it too must have a quantum carrier. That hypothetical particle is the graviton, and in the framework of strings and branes, its nature explains everything. Unlike the particles of matter and light, which are represented by open strings with ends pinned to our brane, the graviton is conceived as a closed loop of string. It has no ends to anchor it. This simple geometric difference grants it a cosmic passport. The closed string of the graviton is free to vibrate not just on our brane, but through the higher dimensional arena known as the bulk. It is the only particle in our universe that is not a prisoner of our three-dimensional slice. This is the elegant mechanical reason for gravity's unique weakness and its ability to whisper between parallel worlds. Its force-carrying particle simply spends most of its time elsewhere, its influence diluted across realms we cannot perceive. This is not just a beautiful story. It leads to a dramatic, testable prediction. If extra dimensions exist and gravity propagates through them, then gravitons should be able to do something no other particle can. They should literally vanish from our brane. In particle colliders like the Large Hadron Collider, scientists smash protons together at nearly the speed of light, recreating the fiery conditions of the early universe. In these collisions, energy is converted into new particles that spray out from the impact point detected by enormous instruments. Most of these particles are familiar: electrons, photons, quarks. But what if, in a tiny fraction of collisions, a graviton is produced? According to the Brane world picture, that graviton, being a closed string, would immediately escape into the bulk. From the perspective of our detectors, it would simply disappear. The collision would appear to violate a sacred law of physics, the conservation of energy. A significant amount of energy would seem to vanish without a trace. This missing energy signature is one of the most tantalizing clues physicists are hunting for in the mountains of data from the LHC. There is another, even stranger signature tied directly to the legacy of Kaluza and Klein. Remember their idea of a tiny, curled-up dimension. In quantum mechanics, a particle confined to a small loop can only have specific, discrete amounts of momentum, like notes on a guitar string. If an extra dimension exists, even a graviton or another particle moving through our brain could have a tiny bit of momentum in that hidden direction. This extra momentum would manifest to us as extra mass. The result would be a series of heavier copies of every known particle, each one representing a different note of momentum in the curled-up dimension. These are called Kaluza-Klein excitations. It would be as if every particle in our world had a series of heavier, invisible twins, each one a shadow cast by its motion through a hidden realm. The LHC is also meticulously searching for the fleeting appearance of these exotic, heavy duplicates. While neither missing energy nor Kaluza-Klein partners have been definitively found yet, the search itself reframes our entire experimental endeavor. We are no longer just looking for new particles in our world. We are building the most powerful microscopes in history to look for footprints, for echoes, and for absences that point to the architecture of everything beyond it. The hunt for missing energy leads us back to the beginning, to a time when the rules of reality may have been written in a far simpler language. We assume the universe has always had the 4 dimensions we know. But what if that is an illusion of our cool, calm, modern cosmos? A radical class of theories suggests the opposite. In the furnace of the Big Bang, at energies beyond comprehension, space-time itself may have been a flatter, simpler place. The number of dimensions we experience could be a product of cosmic history, not a fundamental truth. This is the idea of vanishing dimensions at high energy, a complete inversion of the story we usually tell. We picture extra dimensions curled up small, but here, dimensions themselves disappear as we look back to higher energies. In the first fleeting moments after creation, the universe may have possessed only 2 effective dimensions, one of time and one of space. It was not a voluminous cosmos, but a frenetic, linear reality. As this primordial fireball expanded and cooled, the other dimensions we take for granted, the depth and breadth of our world, slowly crystallized, unfurling like petals from a bud. This staggering notion emerges from the thorniest problem in physics, uniting quantum mechanics with gravity. At the tiny Planck scale, the fabric of spacetime is expected to churn with violent quantum fluctuations, a foam of virtual black holes and wormholes that makes the very concept of a smooth dimension nonsensical. A 2-dimensional starting point offers an elegant escape. In 2 dimensions, gravity becomes dramatically simpler, even trivial in some formulations. The nightmarish infinities that plague the mathematics of quantum gravity in 4 dimensions can vanish, allowing for a well-behaved description of the universe in its first moments. The transition from 2 dimensions to 4 could then be a phase change akin to water freezing into ice. The hot, fluid chaos of the early universe, described by a manageable 2-dimensional physics, underwent a cosmic cooling. At a critical moment, the geometry of spacetime spontaneously organized itself, freezing out the additional dimensions that give our world its rich structure. This reframes our understanding of cosmic inflation, that period of hyper-fast expansion. Inflation may not have been an explosion within a pre-existing 4-dimensional arena. It could have been the process of dimensional unfolding itself, the rapid stretching and solidification of new spatial directions from the primordial template. The uniformity of the cosmos we see in the cosmic microwave background might not be a puzzle to solve, but a natural relic of a time when the universe was too simple, too low-dimensional to allow for complex irregularities. It was a blank slate, and the patterns we see today were imprinted as the slate gained depth. This perspective turns our origin story inside out. The beginning was not a point in a vast space, but the moment space gained its vastness. Time itself may have gained its familiar, flowing character only after this dimensional transition. We are living in the frozen aftermath of a cosmic awakening, where the very stage of reality grew to accommodate the grand play we now witness. That cosmic awakening set a stage, but the play is far from over. A new and baffling act has begun, one where the universe is not just expanding, but accelerating apart at an ever-increasing rate. The mysterious force behind this is dark energy, and its true nature is the greatest unsolved puzzle in cosmology. Could the key lie not in our three dimensions, but in the hidden ones we have been mapping? One provocative idea suggests that dark energy is not a new force at all. It might be a signal, a cosmic symptom of the extra dimensions themselves slowly changing over time. Think back to the curled-up Calabi-Yau manifolds that determine the laws of physics. What if they are not static? What if, over billions of years, these intricate six-dimensional shapes are gradually relaxing, unwinding, or decompactifying? Even a minuscule shift in their geometry would alter the vacuum energy of our universe, the energy inherent to empty space itself. This changing vacuum energy could manifest as the repulsive force we call dark energy. In this view, the accelerating expansion is not driven by something new in our world, but by the slow, grand evolution of the entire dimensional architecture. The universe is not just getting bigger, it is maturing, its hidden geometry breathing out and reshaping the cosmos we can see. Another possibility ties directly to the Brane world models. Our universe is a three-dimensional membrane. Could dark energy be the tension of this brane itself, a constant pressure trying to stretch it flat? Or perhaps it is a sign of our brain slowly drifting or expanding within the higher dimensional bulk, a motion that translates into the accelerated growth of our three-dimensional space. There is an even more dramatic scenario inspired by the ekpyrotic model. Recall the cyclic universe of colliding branes. The phase where the branes are moving apart after a collision is a period of expansion. If this separation is accelerating, it would look exactly like dark energy from our perspective trapped on the brane. The force driving the universes apart in the bulk is the very force causing galaxies to flee from one another here. Each of these ideas reframes dark energy from a mysterious substance to a geometric readout. The acceleration of the cosmos becomes a clue, a dial on a control panel we cannot see, telling us about the dynamics of realms beyond our perception. It suggests that the fate of our universe, whether it expands forever into cold emptiness or cycles into a new fiery birth, may not be decided here. It may be written in the silent, shifting geometry of the dark dimensions, a slow-motion change whose echo is the relentless flight of every galaxy from every other. The relentless acceleration of the cosmos is a slow, cosmic echo, but black holes are where the hidden architecture screams. At their very heart, the fabric of reality is torn apart by a point of infinite density, the singularity. Here, our smooth understanding of space and time completely shatters. But what if, in this ultimate crucible, dimensions themselves begin to unravel? A startling possibility emerges from the mathematics of Einstein's equations. As you approach the crushing grip of a singularity, the effective number of spatial dimensions we experience might not just hide but actually reduce. In the chaotic final moments before the singularity, space may become anarchic, with each of our three dimensions stretching and compressing in wildly different, unpredictable ways. This chaotic mixmaster behavior is described by the BKL singularity, named for physicists Vladimir Belinsky, Isaac Kolodnikov, and Evgeny Lifshitz. Their work suggests that near the end, one spatial dimension becomes overwhelmingly dominant, stretching infinitely long, while the other two contract into a vanishingly small, frenzied pancake. From the perspective of an object falling in, the universe would effectively feel two-dimensional, a wild, oscillating plane hurtling toward oblivion. This dimensional reduction isn't just a mathematical curiosity. It hints that our familiar three-dimensional geometry is a calm, low-energy illusion. In the high-energy inferno of a black hole's core, the true, simpler foundations of spacetime are laid bare. String theory offers a profound reinterpretation of this terrifying endpoint. In its framework, the singularity is not a place where physics ends, but where our limited, three-dimensional description fails. The apparent chaos and dimensional collapse could be a signal that we are finally seeing the full, higher-dimensional geometry. The singularity might be smoothed out or replaced by a complex, multi-dimensional structure, like the intricate folds of a Calabi-Yau manifold, revealed when the energy is high enough to unfurl all the curled-up dimensions. In this view, falling into a black hole would not be a journey to a dimensionless point, but a transition into a realm where all 10 or 11 dimensions of string theory become manifest and significant. The infalling observer wouldn't encounter an end, but a transformation, passing into a landscape where the very concepts of inside and outside lose their meaning in a higher dimensional tapestry. The black hole, then, is not a pit but a portal. Its event horizon is the veil, and its heart is where the true, multidimensional shape of reality is finally unmasked. Portals and singularities are theoretical extremes, but the real test lies here in our own laboratories. For all their mathematical elegance, theories of hidden dimensions must face the unforgiving scrutiny of experiment. This is the great practical hunt, a global effort to find the fingerprints of other realms in the most delicate measurements we can make. One frontier is astonishingly small. If extra dimensions are as large as a fraction of a millimeter, as suggested by the ADD model, then gravity's behavior should change at that microscopic scale. Teams of physicists have built exquisitely sensitive instruments to test Newton's law of gravity at distances smaller than the width of a human hair. They use tiny, vibrating cantilevers or precisely balanced torsion pendulums to measure the gravitational attraction between minuscule masses separated by mere microns. It is a search for a whisper, a deviation from the inverse square law that has held for centuries. So far, no deviation has been found. This silence is not a failure, it is a map. Each experiment that finds nothing draws a boundary, ruling out a larger and larger possible size for these dimensions. The current limits tell us that if large extra dimensions exist, they must be curled up smaller than about 50 microns. The window for them to be large enough to easily detect is rapidly closing. The hunt then moves to the highest energies we can create. Inside the 27-kilometer ring of the Large Hadron Collider, protons are smashed together at nearly the speed of light, recreating conditions a fraction of a second after the Big Bang. This is where we search for the most dramatic signature of extra dimensions, missing energy. If a graviton is produced in one of these collisions, its nature as a closed string could allow it to escape our brane, vanishing into the higher dimensional bulk. From the perspective of the detectors, a significant amount of energy would simply disappear, violating the conservation of energy we expect in our three-dimensional world. Scientists sift through billions of collision events, looking for those where the sum of all detected particle energies falls mysteriously short. They also search for the possible Kaluza-Klein partners, those heavier shadow particles that would be the echoes of ordinary matter moving through a curled-up dimension. To date, the LHC has seen no conclusive evidence of missing energy or these exotic partners. Again, this absence is powerful information. It places stringent limits on the possible energy scale at which extra dimensions could become apparent, telling us they are either smaller or more warped than many hopeful models predicted. Nature also runs its own particle colliders, far more powerful than anything we can build. Ultra-high-energy cosmic rays, atomic nuclei from deep space traveling with the energy of a well-thrown baseball, constantly bombard our atmosphere. Some theories suggest that in the violent collisions these cosmic rays create, microscopic black holes could momentarily form if extra dimensions exist at a high enough energy scale. These black holes would instantly evaporate in a shower of particles, leaving a distinctive signature in our detectors. Extensive searches in observatories like the Pierre Auger Observatory have looked for these exotic showers. None have been found. Similarly, astrophysicists study the evaporation of theoretical primordial black holes and the behavior of gravitational waves, searching for anomalies that might hint at gravity leaking into other realms. The universe itself has provided no smoking gun. The collective weight of these negative results from tabletop experiments, particle colliders, and the cosmos has sculpted the landscape of possibility. Large, flat extra dimensions are now tightly constrained. The most promising surviving models are those with strong warping, like Randall Sundrum, or those where the extra dimensions remain exceedingly small, close to the fundamental Planck length. The hunt has not ended the mystery, it has refined it, forcing the grandest ideas to conform to the stubborn, quiet facts of our three-dimensional reality. The relentless experimental silence is not a death knell, but a call to a different kind of truth. Beyond detectors and data lies a powerful, almost spiritual force that has guided theoretical physics for a century, the pursuit of mathematical beauty. This is not mere aesthetics. For many of the greatest minds, the sheer elegance and internal consistency of a theory is a beacon pointing toward reality's hidden blueprint. And nothing in modern physics exemplifies this more than the drive for hidden dimensions. The equations of string theory and M theory are not just consistent with extra dimensions, they demand them. The mathematics simply does not work in our familiar 4. To a physicist immersed in this landscape, the emergence of 10 or 11 dimensions from the equations feels inevitable, natural, and breathtakingly symmetrical. It resolves ugly infinities, unifies forces with a grace that 4 dimensions cannot match, and paints a picture of reality as an intricate, multidimensional tapestry. This compelling beauty is a powerful argument in itself. History offers a stunning precedent. In the late 1920s, physicist Paul Dirac sought to merge quantum mechanics with Einstein's special relativity. The equation he derived was mathematically exquisite, but it made a bizarre prediction. For it to be consistent for every particle like the electron, there must exist a mirror image particle with opposite charge, an antielectron or positron. At the time, no such thing had ever been observed. It seemed like a mathematical artifact, a beautiful but meaningless quirk of the equations, yet Dirac trusted the beauty. He famously said, "It is more important to have beauty in one's equations than to have them fit experiment." Just a few years later, the positron was discovered in cosmic rays, a triumph of mathematical elegance forecasting physical truth. This legacy haunts and inspires the search for extra dimensions. The profound mathematical necessity of these hidden realms feels to its proponents like a clue of similar magnitude. The theory is too coherent, too tightly woven to be merely a pretty fiction. Its internal consistency suggests it is describing something real, even if that reality is currently beyond our reach. Yet a fierce debate rages. Is beauty a reliable compass or a siren song leading us into a mathematical wonderland disconnected from the physical universe? Critics argue that the human sense of what is mathematically beautiful is subjective, shaped by history and culture. The universe, they caution, has no obligation to conform to our aesthetic preferences. It might be messy, arbitrary, or governed by principles we find ugly or inelegant. They point to the landscape problem. the 10 to the 500 possible universes in string theory as a form of mathematical excess, not elegance. The pursuit of hidden dimensions stands at the crossroads of this timeless tension. Are we discovering the universe's true shape, or are we, like master architects, designing castles in the sky whose foundations may never touch the ground? The answer may lie not in abandoning beauty, but in waiting for the next experimental whisper, the next cosmic clue that could transform a beautiful equation into the law of everything. That relentless pursuit of mathematical beauty often aims to solve a problem of profound ugliness. This is the hierarchy problem, the single greatest embarrassment in our understanding of nature's forces. It is not a minor discrepancy, but a chasm so vast it suggests our entire picture of reality is incomplete. On one side, we have the electroweak scale. This is the energy realm of the particles we know, like electrons and quarks, and the forces that bind atoms, governed by the famous Higgs boson. Its energy is about 250 times the mass of a proton. On the other side, looming like an unscalable mountain, is the Planck scale. This is the energy at which gravity is expected to become a strong quantum force, where the very fabric of spacetime should foam and churn. The Planck energy is a number so immense it defies intuition. It is 10 to the power of 16 times larger than the electroweak scale. That is a 1 followed by 16 zeros. Gravity is weaker than the other forces by this unimaginable factor. Why is there such a staggering difference between the energy of matter and the energy where gravity becomes fundamental? In a universe governed by elegant, unified laws, this split feels arbitrary and unstable, like a pencil balanced on its tip for billions of years. Quantum corrections should naturally drag the electroweak scale up to the monstrous Planck scale, unless some miraculous, fine-tuned cancellation occurs. This fine-tuning seems absurdly unnatural, a cosmic coincidence begging for a deeper explanation. Hidden dimensions offer not one, but two breathtakingly elegant escapes from this dilemma, each using geometry to explain the gap. The DD model, with its large extra dimensions, attacks the problem through dilution. It proposes that the true, fundamental scale of gravity is not at the distant Planck energy, but is actually much lower, much closer to the electroweak scale we observe. The Planck scale we calculate is an illusion, a mirage created by our three-dimensional perspective. Gravity only seems weak because its lines of force spread out into the large, unseen volume of the extra dimensions. Imagine shouting in a small, padded room. Your voice is clear and strong. Now shout with the same force in the middle of an empty desert. The sound dissipates, growing faint as it spreads in all directions. The fundamental strength of your voice didn't change, but its perceived intensity did. In the DD scenario, gravity's true strength is set at the electroweak level, but it is diluted across a higher dimensional desert, leaving only a faint whisper in our three-dimensional world. The Randall Sundrum model takes the opposite, yet equally brilliant geometric approach. It uses warping. In this five-dimensional universe, the fundamental Planck scale is the same on both branes. But the space between them is curved by negative energy, creating an exponential warp factor. This warping acts like a cosmic amplifier or reducer. The electroweak scale on our brane is not fundamental. It is the Planck scale from the other brane, exponentially suppressed by its journey across the warped geometry. Picture two cities at either end of a deep, curved valley. A radio signal broadcast from the city on the high peak starts out strong, but as it travels down into the valley and up the other side to the lowland city, its strength is dramatically reduced by the terrain. The signal's original power was immense, but the warped landscape weakens it by the time it arrives. In this model, we live in the lowland city. The staggering hierarchy between the electroweak and Planck scales is not a mystery of numbers, but a direct consequence of our address in a warped fifth dimension. Both solutions transform an ugly numerical coincidence into a beautiful geometric inevitability. They tell us the weakness of gravity is not a flaw in the cosmos, but a clue to its hidden shape, a signature written in the architecture of dimensions we have yet to fully see. These geometric solutions to the hierarchy problem are not just mathematical curiosities. They leave their fingerprints on the very oldest light in the universe, a cosmic fossil from its infancy. The cosmic microwave background radiation, that faint afterglow from when the universe was only 380,000 years old, is more than a snapshot. It is a canvas where the physics of the first moments, including the possible dynamics of hidden dimensions, was painted in temperature and polarization. If our early cosmos was shaped by extra dimensions, their echoes should be frozen into this ancient light. One of the most powerful predictions involves the pattern of polarization in the CMB. Light from the early universe is polarized, meaning its electric field vibrates in a preferred direction, like sunlight glinting off a lake. This polarization carries a specific imprint from the primordial gravitational waves generated during the universe's hyper-fast expansion, a period called inflation. Theories involving branes or extra dimensions can dramatically alter the expected strength and pattern of these gravitational waves. For instance, in some brane world inflation models, the collision or interaction of branes could produce a distinctive, non-standard spectrum of gravitational waves, which would then leave a unique signature in the CMB polarization, a kind of swirl known as B-mode polarization. Experiments like the BICEP array at the South Pole and the Simons Observatory are scanning the CMB with incredible precision, hunting for these swirls. Finding them with a specific pattern could be a direct signal that inflation was not a simple expansion within our three dimensions, but a more complex event involving the higher dimensional bulk. Beyond polarization, there is the search for non-Gaussianities. This is a technical term for a simple but profound idea. In the simplest models of inflation, the tiny quantum fluctuations that seeded all galaxies are Gaussian, meaning their distribution follows a predictable bell curve pattern of randomness. But if inflation involved more complex physics, like fields moving through a landscape of extra dimensions or interactions between branes, those fluctuations could become subtly correlated in non-random ways. They would leave a statistical fingerprint, a specific kind of unevenness in the hot and cold spots of the CMB map. It would be like finding a faint but deliberate watermark in the static of the cosmic television screen. Analyzing the Planck satellite's exquisite map of the CMB for these non-Gaussian patterns is like forensic archaeology, searching for the tool marks of a higher dimensional sculptor on the first structure of reality. The cosmos may also hold more dramatic relics from its higher dimensional youth. In the fiery, early universe, as it cooled and underwent possible phase transitions in the number or geometry of its dimensions, topological defects could have formed. Think of these as cosmic scars, wrinkles in spacetime that could not smooth themselves out. Cosmic strings are one such hypothetical defect. They would be unimaginably thin, incredibly dense filaments, lighter than a proton but with the mass of a mountain range in every inch stretching across the universe. If they exist, they would warp spacetime around them, acting as gravitational lenses and creating double images of distant galaxies. More strikingly, a cosmic string moving through space would create a sharp, step-like discontinuity in the temperature of the CMB, a clear rip in the fabric of the ancient sky. While no definitive cosmic string has been found, their continued search is vital. In theories with extra dimensions, these strings could be fundamental, higher-dimensional objects like one-dimensional slices of a brane that became trapped in our three-dimensional space as the universe cooled. Finding one would not just be a new astronomical object, it would be a fossil from the era when the cosmos had a different shape, a direct thread connecting us to its multidimensional origins. The silent, cold glow of the microwave background and the vast, empty spaces between galaxies are not empty of clues. They are the archive, and we are only now learning how to read the handwriting of dimensions we cannot see. Yet this archive of ancient light presents a profound and persistent challenge. The most elegant theories of hidden dimensions operate on scales of energy and size that lie far, far beyond the direct reach of our most powerful machines. This leads to a serious and valid criticism, one that strikes at the very heart of the scientific method. If a theory cannot be tested, if it makes no predictions we can check, is it still science? Or has it crossed into the realm of philosophy or pure mathematics? This is the problem of falsifiability. For many versions of string theory and Brane cosmology, the characteristic energy scale is the Planck energy, a realm a quadrillion times more powerful than the collisions inside the Large Hadron Collider. The extra dimensions, if they exist, could be curled up smaller than a trillionth of an atom. Faced with this, critics argue these ideas are not testable in any conventional sense and therefore lie outside the boundaries of empirical science. It is a charge that theorists take with utmost seriousness, and their response forms a multi-front defense of their quest. The first line of defense is the search for those indirect signatures we have already begun to explore. While we may never directly see a curled-up dimension, its existence could leave subtle fingerprints in phenomena we can observe. The hunt for missing energy in particle colliders, for deviations in the law of gravity at microscopic distances, for specific patterns in the cosmic microwave background, or for the gravitational waves from cosmic strings are all searches for these indirect clues. A cosmic string, for instance, is a prediction that emerges naturally from many theories involving extra dimensions and phase transitions in the early universe. Its detection would be a monumental discovery, not because we saw the extra dimension itself, but because it would be a clear, predicted consequence of the higher dimensional physics that shaped the cosmos. It would be like finding a unique seashell on a beach, evidence of a vast, unseen ocean. The second response points to the unexpected predictive power of theoretical tools like the anti-de Sitter conformal field theory correspondence. While the full 10-dimensional string theory may be untestable, the AD/CFT duality allows physicists to use its mathematical machinery to solve real-world problems in strongly coupled quantum systems, like the quark-gluon plasma. When these holographic calculations produce results that match experimental data from particle colliders, it is a powerful hint that the mathematical structure is touching on something true about reality, even if the extra dimensions remain hidden. It demonstrates that these are not just abstract games, but frameworks with genuine explanatory power. Finally, there is the argument from mathematical consistency itself. For proponents, the fact that string theory demands extra dimensions elegantly unifies gravity with quantum mechanics and naturally incorporates the other forces is not a bug, it is a feature. The constraints of internal mathematical consistency are incredibly stringent, weeding out an infinite number of possible theories. In a sense, the theory is being tested every day against the rigid rules of logic and mathematics. The hope is that this web of consistency is so tight, so unique, that when we finally do develop the technology to probe closer to the Planck scale, we will find exactly the structure the mathematics has already outlined. The journey into hidden dimensions, therefore, walks a razor's edge between two pillars of science, empirical evidence and theoretical elegance, holding faith that in the architecture of the cosmos, truth and beauty are ultimately the same. The challenge of too many possibilities forces physicists to search for new geometric arenas. While Calabi-Yau manifolds have been the dominant stage for string theory's 6 hidden dimensions, M-theory's 11-dimensional realm demands a different kind of hidden geometry. This leads us to the world of G2 manifolds, a 7-dimensional shape of stunning symmetry that could provide a more stable, predictive home for our universe. If the 6 dimensions of string theory are curled into a Calabi-Yau space, then the 7 extra dimensions of M-theory must be compactified on something else. That something is a manifold with G2 holonomy, Holonomy is a measure of how geometric objects like vectors rotate as they are parallel transported around a closed loop in the space. A G2 manifold possesses a very special and restrictive type of holonomy that preserves a particular kind of structure. This restriction is so powerful it severely limits the ways the manifold can be deformed. This is the crucial advantage. Calabi-Yau manifolds, for all their beauty, come with a problem: moduli. These are free parameters like the sizes and shapes of the various holes and tunnels in the manifold. Each modulus corresponds to a massless field in our four-dimensional world, a field that could take on any value. This vast landscape of moduli is what leads to that staggering 10 to the 500 possible universes, because each different setting of these knobs creates a different set of physical laws. A G2 manifold, with its tighter geometric constraints, naturally has far fewer of these moduli. It is a more rigid, more determined structure. Think of it like tuning a musical instrument. A Calabi-Yau manifold is like an instrument with hundreds of tiny tuning pegs, each of which can be turned independently, leading to an almost infinite variety of possible sounds, most of them dissonant. A G2 manifold is like an instrument with only a handful of master tuning pegs. Its possible harmonious configurations are much more limited and easier to survey. This rigidity makes compactifications on G2 manifolds profoundly attractive. They offer the hope of a more predictive theory. Instead of a near-infinite landscape, we might find only a handful of consistent ways to curl up the 7 extra dimensions, each one yielding a specific, calculable set of particles and forces in our four-dimensional world. The mathematics suggests these compactifications can naturally include features like chiral fermions, the handed particles that make up our matter, and can replicate aspects of the standard model. Exploring G2 manifolds is not about abandoning the old path, but about mapping a new continent in the same theoretical landscape. It underscores the breathtaking diversity of geometric possibilities. The hidden architecture of reality might not be built from one unique shape, but from a small family of supremely elegant ones, each a candidate for the true geometric heart of everything. This elegant rigidity of G2 manifolds points toward a deeper truth. Not every beautiful mathematical construction can describe a real universe. This realization has sparked a revolutionary shift in how physicists approach the landscape of string theory, a program known as the swampland. The name itself paints the picture. For decades, the focus was on the vast landscape, the 10 to the 500 possible stable vacuum states that could, in principle, represent consistent universes with gravity. But the swampland program asks a more pointed and practical question. Which of these mathematically possible worlds are actually compatible with a consistent theory of quantum gravity? The landscape, it turns out, might be surrounded by an even vaster swamp, a domain of theories that look perfectly fine from a low-energy, four-dimensional perspective, but which cannot be consistently uplifted into a full theory of quantum gravity, like string theory or M-theory. These are dead-end worlds, mathematically possible but physically impossible. The goal of the swampland program is to draw the map, to find the universal principles that fence off the consistent landscape from the inconsistent swamp. It seeks the rules that any viable theory of quantum gravity must obey. One of the most compelling of these rules is the distance conjecture. It proposes a deep link between journeys in theory space and the very structure of spacetime. Imagine you have a field in your theory, like the Higgs field or a modulus field that controls the size of a curled-up dimension. Now, imagine moving a very large distance in the space of possible values for this field. The conjecture states that as you take this long journey, an infinite tower of new particles will appear, becoming exponentially light. Their masses plummet to zero as you travel further. What does this mean in physical terms? This emergence of light particles is a signal of a radical change in the geometry of the hidden dimensions. That long journey in field space often corresponds to a dimension decompactifying or unfurling. One of the tiny, curled-up dimensions starts to grow, becoming large and macroscopic. The infinite tower of light particles are the Kaluza Klein modes, the vibrational notes of particles moving in this newly enlarged direction. Their masses go to zero because the dimension is becoming infinite, and the cost to have momentum in it vanishes. The distance conjecture tells us that if you try to push your theory into a regime where a field value goes to infinity, the theory doesn't just get weird, it fundamentally changes its dimensionality. You cannot have a sensible quantum gravity theory in a regime where a dimension is infinitely large without an infinite number of new particles appearing to signal the transition. This is not just a technical point, it's a cosmic guardrail. It suggests that regimes of parameter space that look perfectly fine in a low-energy effective theory, like having a scalar field with an arbitrarily large expectation value, are actually forbidden in a full theory of quantum gravity. They lead you directly into the swamp. The decompactification signaled by the light particle tower is the universe's way of preventing you from reaching that nonsensical point. Other swampland conjectures further constrain the landscape. The weak gravity conjecture states that in any consistent theory, gravity must be the weakest force. There must always exist some particle with a charge so large that its electromagnetic repulsion overcomes its gravitational attraction. This elegantly explains why we never see stable, extremely charged black holes that could decay via gravity alone, and it places sharp limits on possible particle properties. The de Sitter conjecture casts a shadow on the most popular model for dark energy. It suggests that stable, long-lived universes with a positive cosmological constant, like our own apparently accelerating cosmos, might be incredibly difficult or even impossible to construct in string theory. This has ignited a fiery debate about the ultimate fate of our universe and whether our current understanding of dark energy is complete or if it must be dynamic, tied to a field still rolling toward a different destiny. Collectively, the Swampland program is a paradigm shift. Instead of cataloging infinite possibilities, physicists are now searching for the universal laws that govern the possible itself. It is an attempt to read the hidden rulebook of quantum gravity, written not in the details of any one universe, but in the boundaries that separate the real from the unreal, the fertile landscape from the endless dead swamp. The abstract rules of the swampland find their ultimate test in the gritty, concrete world of particle collisions, while the grand visions of strings and branes often feel light years away from experiment. A class of theories deliberately builds a bridge back to our detectors. These are phenomenological brain world models, blueprints for reality designed not just for mathematical beauty, but to leave clear fingerprints we can actually hunt for. They take the core idea of hidden dimensions and shape it into forms that make sharp, falsifiable predictions for machines like the Large Hadron Collider. One of the most compelling of these is the theory of universal extra dimensions. The name itself is a declaration. Unlike the classic Brane world picture where only gravity roams the bulk, UD proposes a more democratic cosmos. In this model, all the particles of the standard model, every quark, electron, and photon, are free to propagate in one or more small, flat extra dimensions. We are not stuck to a membrane, we are immersed in a higher dimensional space, but one that is still curled up on a microscopic scale. This single change unleashes a cascade of observable consequences. Because the extra dimensions are compactified, particles moving through them have quantized momentum, just like the notes on a guitar string. This means every single particle we know, from the humble electron to the elusive neutrino, must have not one mass but an entire ladder of possible masses. Each rung on this ladder corresponds to a different amount of momentum in the hidden direction. These are the Kaluza-Klein towers, a series of heavier partner particles for everything in our universe. Imagine a piano where every key you normally play has a sequence of higher-pitched, identical-sounding keys above it, each one fainter and harder to strike. In nude, the lightest particle we see is just the ground state, the note with zero momentum in the extra dimensions, but there could be a whole symphony of heavier duplicates waiting to be excited. This creates a spectacularly rich and specific prediction for particle colliders. When protons smash together at the LHC, the immense energy could be used to kick a particle into one of these excited states, creating a first-level Kaluza-Klein partner. But here is the crucial and elegant twist that makes these models so testable. In the simplest UD frameworks, a symmetry called Kaluza-Klein parity is conserved. Similar to the rule that keeps a proton stable, this parity dictates that the lightest Kaluza-Klein particle, often the first excitation of the photon or the neutrino, cannot decay into ordinary standard model particles. It is stable, so what happens when we produce one? The collider event would have a dramatic signature. You would see a spray of familiar particles jetting out from the collision point, their combined energy adding up nicely. But the energy budget would not balance. A significant chunk of energy would simply vanish, carried away by the stable, invisible Kaluza-Klein particle escaping the detector. This is the classic missing energy signal, but with a specific character. Because the Kaluza-Klein partners are produced in pairs due to the conserved parity, events would typically have two invisible particles flying off in opposite directions, leading to large amounts of missing transverse energy. This is a cleaner, more constrained signature than the generic graviton escape of some models. Experimentalists are not just looking for any missing energy, they are searching for the precise patterns, the specific combinations of jets and leptons that would point to the production and decay chains of these Kaluza-Klein towers. They sift through quadrillions of collisions, training sophisticated algorithms to spot the subtle statistical excess that could be the first note from a higher dimensional symphony. The non-detection of these signals so far has already ruled out vast swaths of the possible parameter space for universal extra dimensions, telling us that if they exist, the extra dimensions must be smaller or the masses of the KK partners heavier than we had hoped. Yet the hunt continues because the payoff would be monumental. Finding a Kaluza-Klein partner would not just be the discovery of a new particle, it would be a direct, incontrovertible message from the geometry of spacetime itself, a signal that we are, and always have been, citizens of a larger, hidden world. A stable, invisible particle is one kind of missing piece, but the most profound absence of all lies at the edge of a black hole. This is the information paradox, a crisis that threatens the very foundations of physics, and its only plausible solution points directly to the architecture of hidden dimensions. The problem is devastatingly simple. Quantum mechanics states that information is never destroyed. The exact quantum state of every particle that falls into a star, for instance, is in principle recoverable if you could track all the radiation and debris. But black holes, according to classical general relativity, only have three properties: mass, electric charge, and spin. If you throw a library, a computer, or a person into a black hole, all the intricate information that makes them unique is seemingly erased, swallowed by the singularity. Stephen Hawking made this paradox lethal. He showed that black holes are not truly black, they slowly evaporate by emitting a faint glow of radiation. But this Hawking radiation, he argued, is purely thermal, random noise carrying no information about what fell in. When the black hole finally evaporates completely, all that unique information is lost forever, violating a sacred quantum law. For decades, this stood as an unacceptable impasse. Then came a radical and shocking proposal, the firewall hypothesis. It suggested that the smooth, empty space predicted by Einstein at the event horizon, the point of no return, could not be correct. To preserve the laws of quantum mechanics, there must be a wall of searing energy right at the horizon, a literal firewall that would incinerate anything attempting to cross. This violent solution was born of desperation, trading one paradox for another, as it blatantly contradicted the principle that an observer falling into a black hole should feel nothing special as they cross the horizon. The debate seemed intractable, a war between quantum mechanics and gravity fought at the edge of oblivion, but the battlefield itself provided the escape route. The only framework that has made substantial progress in resolving this paradox is the holographic principle, the very idea that our three-dimensional reality is a projection from a lower dimensional surface. Through the precise mathematical dictionary of the AD/CFT correspondence, physicists can translate the murky, paradoxical physics of a black hole's interior into a well-defined problem on its boundary. In that lower-dimensional quantum theory, there are no singularities, no event horizons, and information is never lost. It simply becomes scrambled and encoded in incredibly complex ways on the boundary, like data being chaotically rearranged on a hard drive. The evaporation of the black hole corresponds to that information slowly and faithfully being radiated back out. From this higher-dimensional holographic perspective, the firewall is likely an artifact of our incorrect, purely three-dimensional picture. The true story involves the bulk, the higher-dimensional space. The information of what fell into the black hole may not be trapped inside a three-dimensional prison. It could be stored in the correlations between the Hawking radiation and degrees of freedom in the bulk, or in the intricate entanglement of quantum fields on the boundary itself. The event horizon is not a fiery wall or a smooth membrane, but a transitional zone where our familiar geometry gives way to a more fundamental holographic description. The information paradox, therefore, is not a sign that physics is broken. It is a beacon. It screams that our three-dimensional view of space-time is fundamentally inadequate for describing quantum gravity. The preservation of information demands a higher-dimensional reality, a cosmic hologram where what seems lost in the depths is actually preserved on the surface, a final, elegant proof that the true workings of the universe are written in dimensions we are only beginning to read. The most radical ideas often begin at the very edge of the map. Beyond the rigorous mathematics of strings and branes lies a territory of pure speculation, where the implications of hidden dimensions stretch into the realms of philosophy, perception, and the unexplained. These are the fringe theories, ideas that push the concept of other dimensions into startling new contexts, often asking not just how the universe works, but how we experience it. One of the oldest thought experiments comes from a 19th-century novel, Edwin Abbott's Flatland. In it, a two-dimensional square encounters a three-dimensional sphere. To the Flatlanders, the sphere is a mystery, appearing only as a circle that changes size as it passes through their plane. This simple allegory is a powerful tool. If a three-dimensional object casts a two-dimensional shadow, what does a four-dimensional object look like in our three-dimensional world? Some speculate that certain unexplained physical phenomena, perhaps even particles that seem to blink in and out of existence, could be the fleeting shadows of higher-dimensional objects briefly intersecting our brain. It is a captivating idea, suggesting that the full, majestic form of reality is forever just out of sight, revealing only distorted slices of itself to our limited senses. This line of thought ventures even further into the subjective. A small but persistent set of speculations propose that consciousness itself is not a product solely of our three-dimensional brains, but an interaction with other dimensions. In this view, the brain might act less like a computer generating a mind and more like a radio receiver, tuning into a field of awareness that exists in a realm beyond our conventional spacetime. Proponents sometimes point to the hard problem of consciousness, the question of why and how subjective experience arises from physical matter, as a gap that a higher dimensional framework could fill. Similarly, historical accounts of psychic intuition or premonition are occasionally reinterpreted not as magic, but as a fleeting, unconscious access to dimensions where time is not linear, where information from potential futures might leak through. It is crucial to maintain a scientifically critical perspective here. There is no empirical evidence for these ideas, and they reside firmly outside the testable framework of physics. Yet they persist because they speak to a deep human intuition that the richness of our inner world might hint at a corresponding richness in the outer architecture of reality. Perhaps the most culturally charged speculation involves the enduring mystery of unidentified aerial phenomena. While the vast majority of sightings have conventional explanations, a fringe theory suggests that a tiny residue of truly anomalous reports could be explained not by extraterrestrial visitors from across space, but by intelligences moving through higher dimensions. The infamous performance of these objects, their apparent ability to accelerate instantly, make right-angle turns at impossible speeds, and vanish from radar, is sometimes described in terms that sound like slipping between dimensions. If our universe is a brane in a bulk, could a technology exist to navigate that bulk, popping into our three-dimensional slice from an unseen direction and then retreating back into the hidden dark? In this speculative scenario, a craft wouldn't fly through our sky so much as it would intersect it, appearing and disappearing not by traveling vast interstellar distances, but by shifting its coordinate in a dimension we cannot perceive. Again, this remains in the domain of science fiction and speculation, a narrative framework more than a scientific theory, but it captures the imagination precisely because it leverages a real scientific concept, the brane world, and extends it into a realm of cosmic possibility. These fringe ideas, from flatland shadows to dimensional consciousness and beyond, serve an important purpose. They remind us that the discovery of hidden dimensions would not merely rewrite our physics textbooks. It would challenge our deepest assumptions about reality, perception, and our place within a cosmos of unimaginable depth. The final frontier may not be space, but the very dimensions of space itself. The final frontier in this quest is not a place but a time. Our journey through 30 theories has mapped a breathtaking landscape of possibility, from curled-up Calabi-Yau shapes to vast, warped branes. But the map is not the territory. The ultimate test lies in the future, in a new generation of experiments and ideas designed to transform speculation into fact. The hunt for hidden dimensions is accelerating, driven by machines of exquisite sensitivity and daring new theoretical leaps. On the microscopic front, the search for large extra dimensions will grow ever more precise. Tabletop experiments are pushing into a realm of almost surreal delicacy. Imagine a device so sensitive it can measure the gravitational tug between two gold spheres smaller than a grain of sand, separated by a gap narrower than a human hair. Next-generation torsion balances and laser-cooled microcantilevers aim to probe gravity at distances of mere microns and then nanometers. They are listening for the faintest whisper of deviation from Newton's ancient law, a whisper that would signal gravity beginning to spread into a hidden dimension just beyond our fingertips. Each null result draws the boundary tighter, forcing the dimensions to curl up smaller or warp more dramatically, refining our picture of what cannot be. The energy frontier will also leap forward. While the Large Hadron Collider has set powerful limits, plans are already underway for its successor, a machine of staggering scale. The future circular collider, if built, would race particles through a tunnel over 50 miles in circumference, reaching energies nearly 10 times greater than the LHC. In its furious collisions, the production of gravitons or Kaluza and Klein partners could move from a faint hope to a tangible probability. It could create microscopic black holes if the energy scale of extra dimensions is within reach, watching for their instantaneous evaporation into showers of particles, a signature written in fire that would change everything. This machine would not just look for new particles, it would attempt to recreate the state of the universe a trillionth of a second after creation, a time when hidden dimensions may have been starkly manifest. Perhaps the most poetic future experiment, however, will listen not to collisions but to ripples in spacetime itself. The Laser Interferometer Space Antenna, or LISA, is a planned gravitational wave observatory that will float in space, forming a triangle with sides 1 million miles long. Free from Earth's seismic noise, it will detect the low-frequency hum of the cosmos. Its hearing is so acute it could tune into the birth cries of extra dimensions. In the universe's first moments, as it cooled from a higher dimensional state, the phase transition that crystallized our three spatial dimensions would have been a cataclysmic event. It would have sent powerful gravitational waves ringing through the fabric of reality, waves with a specific low-frequency signature that has been traveling for over 13 billion years. LISA could hear that echo. It could also detect the cosmic symphony from a network of cosmic strings, the fossilized scars of that dimensional transition as they vibrate and snap. Finding these signals would be the most direct evidence imaginable, a recording from the moment the hidden architecture of our world was forged. Theoretical physics, meanwhile, confronts its own daunting frontiers. The greatest challenge remains taming the string theory landscape. Can the swampland program succeed in charting the true, consistent islands of quantum gravity, leaving the infinite dead-end possibilities behind? This requires a deeper understanding of the mathematics of everything, from G2 manifolds to the non-perturbative heart of M theory. Another profound mystery awaits at the center of every black hole. Do singularities truly exist, or are they all smoothed away by the full, higher dimensional geometry? Solving the information paradox completely may require a full quantum theory of gravity that tells us what, if anything, lies on the other side of an event horizon. The ultimate goal remains a complete, testable theory. The dream is a single framework that not only predicts the existence of hidden dimensions but tells us their exact number, size, and shape, deriving the particles and forces of our world as an inevitable consequence. It would be a theory so precise it could predict the exact mass of the electron from first principles, and so powerful it could describe the fiery birth of the cosmos and the fate of a dying star with the same equations. We are not there yet. The path is strewn with beautiful mathematics and stubborn experimental silence, but the search itself has already transformed our understanding. It has taught us that our three-dimensional world is likely a shadow, a slice, a hologram of something far richer and more strange. Every new experiment, from the quietest tabletop device to the mightiest space-based observatory, is a message in a bottle sent into the dark of the unknown, asking the cosmos one simple, relentless question: what is the true shape of your home? Our journey began with a single, elegant equation and a fifth dimension curled smaller than an atom. It has taken us across a cosmos of ideas, from vibrating strings and floating brains to holograms projected from the edge of reality. We have seen how gravity's whisper could be a leak into a larger dark, how our entire universe might be one page in an infinite book of parallel worlds, and how the very solidity of space could be an illusion woven from quantum threads. These 30 theories are not just a catalogue of possibilities. They are a single, continuous human effort to answer the oldest and most profound question of all: what is the true shape of our home? This quest for hidden dimensions is at its heart the quest for a unified vision of reality, a single story that can cradle the quantum and the cosmic, the infinitesimal particle and the accelerating galaxy within one coherent framework. It is the audacious attempt to read the blueprint from which everything, including the stage itself, is built. That we can even conceive of these geometries, that we can use mathematics to map realms forever beyond our direct sight, is a testament to the power of human curiosity. We are three-dimensional creatures daring to sketch the architecture of 10 or 11. Every experiment, from the quietest tabletop search for gravity's secrets to the colossal detectors listening for the birth cries of the cosmos, is a message sent into the dark, asking the universe to reveal its hidden face. So keep questioning, look at the night sky and wonder not just what is out there, but what the there itself is made of. The fabric of reality is the ultimate mystery, and we are all part of the story of its unfolding. Which of these theories bends your mind the most? Is it the holographic principle, the cyclic collisions of branes, or the simple, beautiful idea that every point in space holds a secret six-dimensional shape? Share your favorite in the comments below, and let's keep exploring the hidden architecture of everything together.